No, I think that's fine. This is sufficient. Yep. Okay. So where we left off before lunch is, I told you that the Green's function in free space is actually a 3x3 matrix because we have intrinsic vector fields. So I just want to take a few minutes to explain kind of how we turn that into an actual number that we put in the Hamiltonian. It's a little bit of just the technicalities of atomic physics. So if you don't remember the details, it doesn't really matter. But I just want to kind of make a plausible argument. So let's just actually take a very simple example of hydrogen. So the ground state is a unique 1s orbital, and then I said that the excited state is 2p, but actually there's 3 degenerate states, which you could call 2p z, and then 2px and 2py. So if I draw the orbitals, 1s is symmetric. 2pz would be a wave function that looks like that, etc. So 2pz is one of them. You could also define things like 2px or even superpositions. So you could take a coherent superposition of px and py. Okay, so there's 3 possible states. And the point is, when you shine in light with a given polarization, you're only going to talk to one of them, really. So for example, my claim is, when I shine in light to excite this atom, I, for example, could choose the polarization of light to be along Z itself. And then, the transition that I'll talk to is actually from 1s to 2pz. Okay? So even though there's 3 states, in practice, you can, there's ways to basically just isolate one of them and get back to your kind of ideal 2-level atom picture. So with that in mind, basically once in lab, you kind of select which one of these states you choose. So basically you can define, in quantum optics, we define something called a transition or dipole matrix element. And then once you fix that in the lab effectively by choosing which one of the excited states you want to talk to, that determines the way that you should use this Green's function. So for example, if I did want to talk to this 2pz state, then it's understood in this kind of spin model here that this E state is the 2pz orbital. And then the particular component of this Green's function that I should use is along the Z direction. So then instead of the entire matrix, I would take just GZZ, which is the Z component of this 3x3 matrix. And if you want to write this out, it's 3 e to the I rho over 4 rho cubed. Sorry. Uh, 1 over rho plus I over rho squared minus 1 over rho cubed. So this part is kind of isotropic, and then there's a term that depends on the angle of observation. So again, the details of the formula don't really matter, but this is just to say that you can project the Green's function into a particular direction. And then it's this GZZ that you would plug into here. Okay, so now the Hamiltonian becomes a normal number again times some operators. Okay. Maybe just to kind of complete the story, if you want to calculate fields, if we were to write down this kind of input-output formalism, your total field is the sum of what you send in plus just some physical coefficients. So again, for example, if we were to choose the transition to be along Z, then we would project the Green's function into Z. Okay, so that's the specific equation. Again, the fact that it's vectorial and so on doesn't really matter. Most of the results. So when I show you numerical results, we do have to pick a polarization, of course, to actually get a number out. But all the physics that I'm going to tell you from here on out doesn't really depend on the polarizations. Okay, so the physics is quite general. There's maybe one more thing I should mention. So let's look at the behavior of this Green's function as R goes to 0. The reason we have to look at that or to talk about it is in this sum, in this effective Hamiltonian, we do have a self term. Okay, so I and J can be the same thing, and so we have a component where we have to evaluate G, where the observation point and the source point are the same. Okay, and so of course that if you have a point dipole, the near field goes like 1 over r cubed. So there's a kind of singularity associated with that. So this thing in the near field has a real component that goes like 1 over r cubed. But then there's also a imaginary component that saturates to a fixed value of I over 2. Okay. So they have very different meanings. So this 1 over r cubed is kind of just saying that. So if I have a Green's function that's real, then this effective Hamiltonian would be Hermitian. So this describes kind of physically that if I have two hypothetical point dipoles and they get closer and closer, the near field interaction would actually diverge. And then when you take it on the same point, formally within this point dipole approximation, it would diverge. The real story, though, is that a real atom is not a point dipole. This kind of divergence, which appears in many forms in physics and field theories, is just something they have to kind of normalize out. So physically, what this describes is a renormalized resonance frequency of the atom. In practice, what it means is that when you call omega naught, so there's the omega naught that we call as the resonance frequency, that will already include this renormalization. And then in practice, if you really want to use these equations, renormalization is just a fancy word to say ignore it. So we'll set it to 0, right? So then, when you put it into a computer, you don't put in any kind of infinities. You just take that term out by hand. But this kind of imaginary part, the fact that you get 1/2, that you do keep. Okay. And the reason you keep that is quite simple. So if we just have n equals 1 atom, then our effective Hamiltonian would just be minus g sorry, I left out a so the way I normalize the Green's function, the free space spontaneous emission rate comes out as a prefactor. Okay, so sorry, I didn't include that earlier. So then if I have just one atom, this kind of this spin model turns into G minus gamma naught, G of R omega naught. And then if I have just one atom, sigma, the raising operator times the lowering operator of the same atom, is just the excited state population. And then by my prescription here, if I evaluate the Green's function at the same point, I should ignore the diverging real part. I should include the imaginary part. And then what you get is minus I gamma naught over 2 sigma EE. So the interpretation is that the excited state has an imaginary energy at decay rate, which is exactly gamma naught, the spontaneous emission rate of a single atom into free space. So it's a very indirect way of deriving single atom spontaneous emission. Okay, so just to summarize, the Green's function formalism should, in principle, be applicable in free space. Here's our effective Hamiltonian, or if you want, you could write back the full Lindblad master equation. And then, the spirit in which we're going to use is the following. So even if you're not used to seeing this Hamiltonian, the fact that it's a Hamiltonian, you just apply the usual rules of quantum mechanics. So for example, if you give me a given number of atoms in a Hilbert space, I can go and at least numerically diagonalize this, or maybe in some cases analytically do it. Once I know, I can also solve the dynamics via the Schrodinger equation or the density matrix. And then, it's normal quantum mechanics. If you give me a density matrix or a state, you can calculate any correlation function you want of the atoms. And in particular, if you want to go and construct any field correlation, you just apply this formula here. So you turn any field correlation function into a problem where you have to evaluate atomic correlation functions. Okay? So in principle, it's just completely textbook quantum mechanics. The only difference is that the Hamiltonian is a little bit strange compared to what you're used to dealing with. So those are the kind of equations that we'll be trying to solve. And so, from there, I'll switch now to slides and actually just kind of show you some of the both numerical and analytical results. The reason I switched to slides is also partly because, in principle, you can go and try to analytically work out on a blackboard what these answers are. Those calculations are straightforward, but they can become a little bit tedious. But what we'll find actually is that the final results, you can just also understand a lot of them by very simple intuition. Okay, so the mathematics, we're always solving this spin model. The final result, you could explain with very simple arguments independent of any complicated spin physics. Okay? Any questions on? Depends on how you phrase it. So the way I formulated the current spin model, it only includes so-called energy conserving terms. So I would have to, the way I excite an atom is I absorb a photon. And so if that's the limit of your atom-light interactions, then what I'm saying is completely true for Rydberg as well. So in some Rydberg experiments, they do, for example, have two different Rydberg levels, an upper one and a lower one, where they can exchange excitation. Exactly through the same process of photon emission and reabsorption, although it's usually in the near fields. So on the other hand, when I said that the Rydberg interaction gives you this 1 over r to the 6, it's actually coming from a separate term. So if you really write out the full atom-light interaction, it also allows for so-called counter-rotating terms, where you can go from the ground state to the excited state and emit a photon, which in practice is a virtual photon. So then there's also a process to integrate out the photons in that case. You get you get a new term in the spin model, which is exactly this 1 over r to the 6 interaction. So in principle, it does come from integrating out photons, but it comes from the so-called non-energy conserving terms that I didn't really talk about, that I didn't really care about for my purposes. Any other questions? I'm not sure if I'm sharing or not. I'm not sure if I'm sharing this screen or not. I am? Okay, great. Okay, great. Thanks. Okay, so I'd like to now just again show some of the kind of I'll give you a sample of some of the kind of physics and consequences that come out of this spin model. So let me just start with some basic phenomenology. So even at the single photon or classical optics level, these are things that you would already get just by honestly including wave interference. So one thing we'll study is a 1D atomic chain, show that acts as an optical waveguide for light. We'll also show that if you have a 2D array with a sub-wavelength lattice constant, that can in principle act as a perfect mirror for single photons. So you can have an atomically thin surface, which is in principle 100% reflecting. Putting together a collection of atoms is a very expensive way to make a mirror, right? But then, what you could try to do is kind of functionalize it. So then we'll discuss how to use arrays of atoms like this to construct a quantum memory for photons and a photon-photon gate. So the protocols look very similar to what I already presented for free space. What we hope to show is that by honestly including wave interference, which the spin model does, we'll hopefully be able to do better than the textbook answer that I presented this morning. And then at the end, I'd like to give some kind of sampling of many-body or emergent phenomena. Honestly, we don't know very much about this regime, but I hope to convince you that there's a couple of examples where it seems like the physics, there's room for a lot of interesting physics to occur. Okay, so So I would love to be able to tell you that all the things I'm telling you now were because we have some brilliant insight and we were geniuses. Okay, that's actually not the case. We were very stupid and we were very lucky. So actually, let me show you historically the stupid lucky calculation that we did. So this is exactly the first calculation that we did. that really kind of convinced us that, oh, there's really something that we don't understand and something missing in the textbook. Okay. So again, here's the kind of spin model in general. In this case, we'll take atoms, a two-level transition where the dipole matrix element or the polarization is along x. Okay, so here's our Hamiltonian. And now if we actually want to solve any particular example, we have to specify a geometry, right? Because this Hamiltonian has specific atomic positions. And so what we literally did is we said, we'll consider a 3D, so we live in three-dimensional space, but we'll consider just a line of atoms, a 1D chain, a lattice with a well-defined lattice constant d. And we'll let the number of atoms be finite. So if we have n two-level systems, this Hilbert space of spins would be 2 to the n. So we weren't even that ambitious. Let's say, well, let's do something simpler. Let's just consider the space of one excitation. So this Hamiltonian commutes with excitation number, right? Because I have to destroy an excitation on one atom and add an excitation on another. So let's just look at the single excitation space. In that case, instead of 2 to the n, your Hilbert space is just n, right? Because either the first atom could be excited, the second one, the third, and that forms your n-dimensional Hilbert space. Okay? And then within that Hilbert space, your Hamiltonian is just an n by n matrix, where the components are just the Green's function elements themselves. Okay? So this is a calculation that you can put into a computer and program up in half an hour. And then, well, we're stupid. So what do you do when you have a Hamiltonian? You can try to diagonalize it. So if you have an n by n Hamiltonian, you get n eigenstates. So I'll label these eigenstates by alpha. So this is just an index that runs from 1 to n. And this Hamiltonian is a full rank matrix. So you'd expect that when you diagonalize, your eigenstate is not just going to be a product state of the fifth atom being excited, but it's going to be some superposition. And so I kind of heuristically write it out this way. So given any given eigenstate alpha, there's going to be some arbitrary superposition of atom j being excited with some amplitude Cj. Okay, so this is just what the computer would spit back at us. If you were to take one particular eigenstate at random, you can plot out actually the amplitudes. So what I'm plotting here is the amplitude of atom j to be excited along the chain. This particular eigenstate looks like kind of half of a standing wave. Other eigenstates could look more complicated. And then you can look at eigenenergies. Okay? And so in this case, because we have a non-Hermitian Hamiltonian, our energies can be complex. So we can separate it into a real part and an imaginary part. The real part is going to describe a shift. So each one of these eigenstates you can think of as a normal mode of the system. And each one of these normal modes could have a resonance frequency that's different than the bare atomic resonance frequency. So that's what this real part of the energy describes, delta omega alpha, that's the shift. And then the imaginary part will describe the decay rate of that superposition, of that one collective excitation. And in general, that might be different than the single atom spontaneous emission rate due to some kind of interference effects. Okay? So what I'm going to show you next, we're just going to do it numerically for some moderate number of atoms. Actually, in the exercise for tomorrow, we're going to try and solve the problem of n equals 2 atoms exactly. Okay? So you get a better sense of how this diagonalization works. Okay, so here's the numerical results. To make it concrete, we can take 30 atoms. And what we're going to do is we're going to do a set of simulations where every time we take 30 atoms, but we change the lattice constant. So the lattice constant is what's being plotted on the x-axis here. On this particular plot here, what I'm plotting is the frequency shift. So this delta omega alpha, or the resonance frequency of each normal mode. So the way to think about it is, at the first simulation, I could choose a lattice constant of 2.1 lambda, which is relatively a large spacing. I diagonalize, I get 30 eigenvalues. And so along this vertical cut, I plot in 30 points. So the 30 dots are too close together that you can't see every one. And then I can do the same thing. I can plot out the 30 different decay rates of these eigenstates in the same way. And the point is that you see that for this particular lattice constant of a few wavelengths, the range of decay rates of these eigenstates, okay, they're not exactly 1, or they're not exactly the single atom rate, gamma naught, but they're all pretty close. So they're 1 plus or minus a small amount. And similarly, if I look at the kind of frequency shifts of these resonances, they're some small fraction of the natural line width of the system. Okay, so the atom knows a little bit about multiple scattering of light, wave interference, but more or less each one of these eigenstates looks kind of like the independent or isolated atoms. Okay, so then I can kind of keep doing the calculation, taking smaller and smaller lattice constants. Okay, so what this shows is that at large distances, the spin model and interference, doesn't really seem to make a difference. And then you keep making the lattice constants smaller and smaller. You see that the range of decay rates, the deviation from 1 gets bigger and bigger. Similarly, the range of resonance frequencies gets bigger and bigger, bigger and bigger. And then once you go to a lattice constant that's below lambda over 2, you see very qualitatively different behavior emerge. Okay, so for 30 atoms, if I choose the lattice constant to be less than lambda over 2, I get a range of decay rates for these eigenstates. So some of these eigenstates apparently are able to emit light, spontaneously emit light just fine, but there's some subset of eigenstates whose decay rates go nearly to 0. So these are so-called subradiant states. Okay, so that's kind of weird, because in the Maxwell block equations, they say that if I have one excitation, it's always going to decay at a rate gamma naught, and there's nothing I can do about it. And now all of a sudden, this calculation is telling me that somehow an excitation is able to hide within the atoms for a very long time and not turn into a photon radiating into 4 pi. Then you can ask, well, how small is small? You can do, after years of training, what you can learn to do as a physicist is to replot things on a logarithmic scale. Okay, so we'll take this same plot and just redo it on a log scale. And what you see is that, actually, for 30 atoms, there's some states that can live 1,000 times longer than what the Maxwell block equations predict. And then you can go look at kind of the scaling numerically. What you find is, so now let me index the eigenstates in a way such that in order of increasing decay rates. So alpha equals 1 is the state that lives the longest. Alpha equals 2 is the second longest living state, and so on. And what you find numerically is that the decay rates of these states, they scale like this index alpha squared. And maybe more importantly, as you increase the length of the chain, the number of atoms, this decay rate drops like n cubed. Okay, so you make a longer and longer chain. This excitation somehow finds a better and better way to avoid being emitted into a 4 pi photon. Okay. So what the heck is going on there? Well, so apparently what it shows is that this kind of independent emission assumption that's built into the Maxwell block equations somehow becomes very bad once atoms become separated by short distances, where the short really means kind of on the wavelength scale. Okay, and in that case, these interference effects become very important, and I really can't think of atoms as being independently emitting objects anymore. Okay, so that's the inference from these numerical plots. Whether or not we have any kind of physical intuition for it or not. So I think that's a calculation that we did, 8 years ago, and this kind of these points down here really just kind of piqued our interest and forced us to ask, what in the world is going on. Yep. Well, it's not stupid. It's just like, okay, absent anything better to try, let's ask a computer what the answer is, and. No, it is very cool. So, I mean, yeah. So, I mean, I guess we were lucky in the sense that, I mean, I don't know, we could have plotted disordered atoms, calculated disordered atoms or anything else, maybe then it would have been much more mysterious. So the fact that we did this particular calculation, I mean, I guess the point is, theoretically, you kind of have a sense that you run into something cool if there's something in the plot that you just completely don't understand, right? It's not because you put in a minus sign in your code when you should have put in a plus, right? Okay, so now let me kind of explain. Oh, sorry.
I was wondering, but if the lattice spacing becomes very, very small, don't you have additional terms in the Hamiltonian, like the wave functions of the atoms that are overlapping, and so you could have also processes? Did you investigate what happens in that scenario? Or
Depends on how you phrase it. So if you say that, for the moment, I put aside any kind of realistic implementation. So for example, my atoms are really just perfectly pinpoint particles. So then you could say, well, with solid state emitters like a quantum dot, okay, that's a good approximation. If you say that these are actually cold atoms in optical lattices, then atoms could tunnel. And then you can ask what's the consequence of that. It's not something that we studied specifically, but I do think it's a kind of interesting problem because it might be that even the light scattering and the way it responds to light knows about whether you're in a, for example, a mod insulating state or superfluid state, et cetera. There's another problem you can ask is even if you say that my nuclei are perfectly pins, when the atoms get very, very close, kind of like nanometer scale, so that's kind of much more close than you could ever get with optical lattices. But when they're nanometer scale, even if the nuclei are perfect delta functions, your electron orbital, of course, has a finite size. And then you could have what you might call kind of quantum chemistry or solid state effects. So an electron could literally just tunnel over to the next nucleus. That actually we have studied. And maybe to give a kind of preview of things to come, there's a kind of weird question you can ask. So maybe I'll kind of spoil the future slides a little bit. But so here's a game you can play. Like try to take any optical material you can think of. So when I say optical, let's consider visible wavelengths or telecom. And if you can show me in literature a material with a refractive index of 10 or bigger, I'll buy you lunch tomorrow. Okay. So then the question, the follow-up question is like, why is the refractive index of every material so small? In particular, if you think of any other material property like specific heat, conductivity, et cetera, that varies by orders of magnitude, going from one material to another. It certainly depends on whether your material is ordered or disordered, insulating, conducting, solid, gas, et cetera. So why the heck is it that refractive index, to lowest order is independent of any of that? So that actually seems to be a very subtle question and challenging one. And it seems like the reason an answer is very elusive is exactly because to solve that problem, you have to understand the problem of non-perturbative multiple scattering. So we did try to attempt to answer that particular question. And in that case, if you want to talk about refractive index of real materials, you have to combine not only this kind of non-perturbative multiple scattering, which is encoded in this Green's function, but also kind of real quantum chemistry effects that electrons have finite size, they can interact with one another, et cetera. Any other questions? Okay. So then to try and figure out what might be going on, we then realized that a conceptually simple limit should be just to not take finite atom number, but to go straight to the case of infinite atom number. So again, now where it's infinite atom number, but only one excitation. So because we have a periodic system and single excitation physics, we know that all of our eigenstates have to obey Bloch's theorem, okay? Which means that any eigenstate I can index with a Bloch wave vector k, and the form of that eigenstate has to look like the following. It's a superposition where atom J is in the excited state and all the other atoms are in the ground state, with a relative phase e to the ik zj, right? And so once you know that every eigenstate has to look like that, you can plug it back into the time-independent Schrodinger equation and try to calculate the eigenvalue or eigenenergy. And generically, you're going to get a band structure, but it's going to be a complex band structure because we have a non-Hermitian Hamiltonian. So formally, actually, you can just say on formal grounds that the eigenenergy or eigenvalue associated with this block wave vector, again, you can separate into real and imaginary parts, but that complex energy is going to be the discrete Fourier transform of the Green's function in real space. Okay. So you can try to do that calculation. There's no simple closed form for it. But you can try to do it numerically, for example. And you get something like the following. So what I'm going to plot here, just for the sake of argument, is the real part of the energy. And then later on, I'll talk about the imaginary. So first of all, what properties does any general band structure have? Well, first, the band structure is only really uniquely defined, or I only need to define it within the first Brillouin zone. Okay, so the range of block wave vectors goes from minus pi over the lattice constant to pi over the lattice constant. And then, without any kind of serious work, one thing you can kind of conclude is that, I expect my band. So if I have one excitation, I expect the band to more or less be centered around the bare atomic resonance frequency, omega Eg. And then when you do the calculation, you'll get some particular band structure. The particular shape doesn't matter. But expect this band to be reasonably flat, okay? Because the scale of interactions in this Green's function is set by the single atom spontaneous emission rate. Okay? So a general feature like this you can kind of guess or hypothesize on very general grounds. But just kind of plotting that in, you can get a lot of intuition. So let me show you how. So the next thing you can plot in is just the dispersion relation of light in empty space, omega equals ck. And it turns out that this line of omega equals ck divides two very different types of behavior. So in particular, I'm using the spin model to calculate the eigenstates of just the atoms. But in principle, if I reconstruct the fields, I know that the field also has to obey Bloch's theorem. So in other words, if I choose a particular eigenstate with a Bloch wave vector of k, then when I calculate the field that's produced by that set of atoms, the electric field, along the direction of the chain, it should also have a wave vector dependence given by the same e to the ikz. Okay, so both the field and the spins obey Bloch's theorem. But there's a key difference, which is whereas my spins live in a 1D chain, my field lives in a 3-dimensional space. Okay, so this Bloch wave vector k really only gives me the projection of the wave vector along the direction of the chain. So left over, I still have a kind of transverse wave vector, which describes the field profile in the transverse directions. And I mentioned the other day that to satisfy Maxwell's equations, the components of k cannot be arbitrary. They have to satisfy this dispersion relation where the in-plane k squared plus the out-of-plane k perpendicular squared equals omega over c squared. And then similar to the argument I made the other day, if k itself is bigger than omega over c, then the only way to satisfy this dispersion relation is if the perpendicular component of the wave vector is imaginary. Okay, so let's go back to this plot and understand what that means. So let's take this kind of dispersion relation here. This describes different spin wave modes in my system. If I take this particular solution here, you see that the in-plane k, or the Bloch wave vector, is smaller than omega over c, which means that the corresponding transverse wave vector is real. It's a radiation field. Whereas if I take a solution out here, k is already bigger than omega over c, which means the electric field being emitted by this guy is evanescent because it has an imaginary value of k perp. So to say that another way, the set of modes within here, within the so-called light line or light cone, they generate intrinsically radiation fields, and radiation fields carry energy, which means that this atomic excitation can now radiate energy away to infinity, and that should fundamentally lead to decay. So these states here should have a decay rate in general that's not 0. And conversely, these modes here, they can only generate evanescent fields, which cannot carry electromagnetic energy out to infinity. Therefore, this atomic excitation can't do anything. It has to live there forever. So this decay rates of these states beyond the light line for an infinite chain have to be exactly 0. So this kind of language of evanescent and so on, it's exactly the same language I used to describe guided modes of optical fibers before. And so what you see is that this kind of simple calculation leads to a very simple statement, which is that when you have an ordered chain, an infinite chain, this subradiance, this ability of an excitation to live forever, is completely equivalent physics-wise to optical waveguiding. So this atomic chain is nothing more than a fancy optical fiber or photonic crystal waveguide, if you want. And that's a really kind of weird statement if your reference point is the Maxwell-Bloch equations. Again, Maxwell-Bloch says you excite an atom, it's going to decay, there's nothing you can do about it. What the spin model says, even at this very simple level, is no, an atomic excitation can live forever. So then you can ask, well, what are the conditions in which this is true? The only condition is really that this plot is accurate. So in particular, there have to exist. So you draw this dispersion relation omega equals ck, and these subradiant modes are the ones that live out here beyond the light line. So for these modes to exist in the first place, what you see that has to be true is that your atomic resonance frequency, omega Eg, has to intersect the edge of the Brillouin zone at a lower frequency than omega equals ck. So in that case, part of this blue dispersion relation is guaranteed to live beyond the light line. So if you take that condition on resonance frequencies and convert it back to distances, you see that's completely equivalent to the lattice constant being smaller than lambda over 2. So that explains the kind of finite size numerics that we saw earlier. Any questions on that? Okay. Yeah.
So then in the open boundary case, you see this n at the -3 expression. But for example, you have some, okay, you have n very large, and then so you have some disorder, maybe you miss some atoms in the middle. How is the protection then? It's still
Right. So I think we numerically studied in the past. So let's say, for example, that you disorder your atoms by some Gaussian distribution, and that's called the width of the distribution delta. If I'm not mistaken, then kind of statistically, the smallest decay rates would go like this width of the distribution delta squared. But I'm not 100% sure of that.
But it's still very small. You can make it very small.
Yeah, yeah. Okay, so now if I guess, once we realize that this kind of phenomenon of subradiance is really just kind of optical fiber physics, we can also come up with very simple arguments why, in a finite size system, you now have a non-zero decay rate. In particular, if you have an optical fiber, it guides light in principle perfectly, so you can't see light, coming from the bulk of the fiber. But then if you take a fiber and you cut it, all of a sudden light can spray out. And of course, that's the principle between these kind of fancy optical fiber lamps that you can buy. And then you can actually do the calculation. So you go back to this n equals 30 atoms. You take one of these subradiant states. You reconstruct the fields, using this input-output formalism. And you did see that all the light that's being emitted is coming out the ends, exactly like a cut fiber. So, of course, we took a very particular system of a 1D chain. And I'll really only explain specifically to you how subradiance emerges in that case. But you might suspect that actually the phenomenon of subradiance might be rather general. So even in higher dimensional arrays, maybe even in disordered systems. But then if it's quite general, you might ask, well, how come no one has seen it? So now people have kind of seen it. But how did we manage to go 40 years with the Maxwell block equations without people noticing experimentally that there is something funny? One nice thing about this kind of just continuing the same line of argument is, you start to appreciate these subradiant states are almost by definition decoupled from free space radiation. So when you say that you see something in quantum optics with atoms, what that almost means inevitably is that you have a collection of atoms, you shine in a laser, and then you're looking for some response. But a laser, by definition, no matter which direction you shine it in from, is a radiation field. Okay, so that laser is always going to live within the light cone, but then these exotic states live outside. So even if they perfectly exist, you could perfectly well miss them in any experiment. So if we want to start accessing these subradiant states, what can you do? Well, since we now understand that subradiant states, at least in this 1D chain, are just guided modes, one way to naturally excite guided modes is by another set of guided modes, in particular an optical nanofiber. So I already introduced the nanofiber setup. Again, you can start with a normal glass fiber and pull it until the center becomes very thin, just a few hundred nanometers in diameter. Then you can use actually the guided modes themselves to form an optical lattice to trap atoms. And then shine resonant light, and then the resonant light would also couple to the atoms relatively efficiently. So one catch I should say is that, again, in the current experiments, you only have about 50% filling, whereas the kind of picture I showed you before is really kind of a perfect atomic chain. Okay, so that's just kind of, so aside from the fact that experiments can't literally see what we're describing at the moment, let's just kind of conceptually suppose that in a nanofiber you could magically get 100% filling somehow. And then remember also in a nanofiber, these nanofibers give you a reasonable coupling to light, but not super efficient. So the way to characterize that is if you have one atom, just one atom, and you excite it, about 5 or 10% of the time, a photon is emitted into the guided modes, but then the rest of the time, 90% of the time, that photon is still emitted into 4 pi. Okay, so now consider a fiber with really perfect unit filling. So I have a lattice of atoms, perfect lattice coupled to the nanofiber. So now what I've drawn here is the dispersion relation of just the atomic chain alone. And then, again, by definition, a fiber mode is a guided mode. Okay, so its k vector also has to sit beyond the light line. Otherwise, the fiber would just radiate into free space, and you wouldn't be able to transport energy at all. And so the point is that it doesn't really matter what the specific dispersion relation of the fiber mode is, but it has to live beyond the light line. And so somewhere, inevitably, your atomic waveguide and your normal nanofiber waveguide, those dispersion relations have to intersect. And the point where they intersect, then all of a sudden, this kind of atomic guided mode and the nanofiber guided mode should be able to perfectly interact with one another. Okay. So if that occurs, then I've actually kind of subtly changed the concept of the physics on you. So subradiance I guess if we want to kind of make a definition for it, that's a state where the atomic excitation will just kind of hang around forever and never dissipate. So in the case, in the previous case where the fiber mode and some intersects with some set of k vectors of the atomic modes, now the atomic modes will perfectly radiate or couple to the nanofiber. Okay, so they're not subradiant anymore. But it turns out if you want to build an efficient atom-light interface, like for a quantum memory or photon-photon gate, etc., that situation is perfect. It's exactly what you want. So we call it, not subradiance, but selective radiance. And the reason is, in a cartoonish way, the following. So if I take a chain of atoms with one excitation, what this kind of coupling to the nanofiber does is it gives you a collective enhancement of emission into the nanofiber. So even though you have one excitation, that excitation can now radiate efficiently into the nanofiber. You have a similar notion of collective enhancement in free space. So the whole concept upon which atomic ensemble physics is based is that of collective enhancement. When you have more atoms, you can do better. But then, in this kind of system where we honestly keep into account, track the kind of 4 pi emission and all the interference, because the k vector of these modes is still beyond the light line, those particular set of modes should not be able to radiate into free space. Okay, so again, they talk to a preferred set of modes, these guided modes, which you can perfectly catch, detect, generate, and so on. But then through destructive interference into 4 pi, you expect that, essentially it's very improbable that you ever lose an excitation. Okay? And then in free space, we saw that, the smallest decay rates in the free space could scale like 1 over n cubed. So if that physics is maintained in this kind of nanofiber system, then we can try to construct a branching ratio of information, so n times gamma 1d, divided by the cooperative decay rate into free space, which we might guess goes like 1 over n cubed. And now all of a sudden, instead of a linear scaling with atom number, which is what the optical depth is, I would have a scaling of this branching ratio that scales like number of atoms to the 4th power. Okay? So if the branching ratio really is the key figure of merit for any application, now all of a sudden, I can beat what the textbook told me. So aside from the mathematics and the details, which I'll go into later on, this slide here is really the essence of quantum optics with arrays and trying to encode applications in a way that is much more efficient than what the textbook told you was possible. So this is a really important idea. So if anyone has any questions, maybe now's a good time to ask.
From what I understand, that was developed based on this numerics you've had. So is there any analytical understanding why particularly n cubed, or?
Yeah. So there's different degrees to which you can argue it, but maybe minimal version is if you believe that generically, if you have a long enough chain, you might believe that your eigenstates are more or less going to look like standing wave patterns. So then so the point is if you have a standing wave, but then all of a sudden just cuts off at the end, then if you take that so if you take a smooth function, but then all of a sudden cut the ends of it, when you Fourier transform that thing, you have actually a lot of Fourier components. And some subset of those Fourier components will live within the light cone. And then if you calculate the weight, how much weight in the Fourier components do you have within the light cone, and calculate the corresponding emission rate, you would get this 1 over n cubed scaling.
Sorry, but what do you mean by a light cone?
Oh, okay, yeah. So the statement is really that. So I argue that if you have k vectors within this triangle, within the light cone, they should radiate. K vectors out here should not. So in other words, the decay is really not in position space, but in momentum space. So if I can understand the momentum content of any wave function I have, I can calculate how much weight there is within this light cone, and that would give me the dissipation. So this 1 over n cubed just comes from that.
Okay, I see. So it's basically that when you cut the function, like in order to expand it in like Fourier series, you need like many high frequency kind of components.
Exactly.
Okay, I see. Okay, perfect. Thanks.
Yep.
I was wondering about the role of jumps. Like here, it's purely effective, and I remember 2 days ago,
Right.
Time notion of time is a little bit messy. You said that in some scenarios you can neglect those jumps, but it's always be the case. Are
Right.
there scenarios where are important?
So in this case, you can ignore the jumps because you're in the single excitation manifold. So when you lose the excitation, you know that all your atoms are back in the ground state. So you can effectively reconstruct the whole density matrix from the wave function itself. So yeah, this is one of the 2 limits in which it's sufficient to talk about only the effective Hamiltonian.
I mean, to rephrase this, it means you already know that you are out of what you wanted.
Exactly,
like,
yeah.
Okay, perfect. Thank you. Follow-up question. So it means if we go to the multi-excitation regime, it could be the jumps have to be taken into account?
Generally, yes. So especially, so in the end, I'll show you many-body dynamics. And there you do have to, so then essentially, when you have a larger and larger system size and more excitations, a jump is almost inevitably going to occur. So you really have to figure out where your population is going to understand the physics.
Thank you.
Okay. So to really understand, like, so I kind of mentioned a hypothesis that when you couple atoms to a nanofiber, you can dramatically improve this kind of branching ratio of light that's emitted into the nanofiber as compared to 4 pi. So now what we can do is we can try to numerically calculate that. Again, all we have to do is we have to find the Green's function for this particular setup. So in particular, we have a cylindrical dielectric fiber surrounded by vacuum. Okay, so this is just it's an ugly exercise in Bessel functions, but you can actually calculate the electromagnetic Green's function for that particular system. Okay. Then what we want to do is, well, to quantify that, we have to choose an application. The simplest one is a quantum memory. So again, we want to take, with this particular nanofiber setup, this idea that we send in a single photon. We want to ask with what fidelity or what efficiency can we really coherently map it into a collective atomic excitation. So again, we're just going to study EIT. So we consider a set of atoms which are initially in the ground state. We have a single photon, which is guided in the nanofiber and coming in to excite the atoms. We take a 3-level system. So we couple this excited state to a 3rd level via classical control fields. And then we want to calculate the efficiency. If we try this, what's the probability that we actually kind of convert this photon into a single collective atomic excitation? So to give you some flavor of how we do that in practice, it turns out to be easier. So you can exploit the fact that in principle this is unitary, right? So it can map a photon to an atomic excitation or vice versa. It turns out the opposite way is a little bit easier to calculate. So the idea is the following. Like, let's start with one atomic excitation. So we start with a normalized wave function where there is one excitation distributed somehow over my n atoms. I'm then going to calculate the Schrodinger dynamics under my effective Hamiltonian. So now I know the time-dependent wave function of the atoms. Once I know the time-dependent wave function, I can calculate any correlation function of the fields that I want. In particular, I can calculate the intensity of light emitted into my nanofiber, starting from my initial time out to infinity. So this is basically the probability, this is the total probability that I emit a photon into my nanofiber as opposed to 4 pi. So if it's perfect, this probability would be 1. In general, it's not going to be 1. this probability also depends on my initial state. So then what I can do is I can try to optimize over all these possible amplitudes. Okay, so that's the conceptual thing that we're trying to do. It turns out that you can turn this into a nice, more efficient scheme, so you don't literally have to search over this huge space, but conceptually, that's how we calculate things. And when you do that, here's the answer. So what I'm plotting here is the error of the quantum memory as a function of atom number. So to compare, if I took the Green's function for the nanofiber, and I just put in by hand single atom spontaneous emission, so in other words, the Maxwell block equations, I get an asymptotic scaling that's 5.8 divided by optical depth. That's the known result from textbooks or from papers. And then if I do the same calculation with a full spin model, fully accounting for wave interference, you see that you do better. And numerically, asymptotically, that seems to scale not like 1 over atom number, but 1 over atom number squared. Okay, so this shows that quantitatively, wave interference does make a difference, and it justifies this idea of selective radiance. But now let's be greedy. Okay, so let's say, well, 1 over n squared doesn't seem that great, actually. Because in particular, even if I go back to the usual Maxwell block equations, I already have a 1 over n scaling, right? Because I have this notion of collective enhancement into my nanofiber. Okay, so one of these factors of 1 over n I'm just getting for free, even in the Maxwell block equations. Okay, so if I'm getting 1 over n for free, that means this kind of suppression of 4 pi emission is only contributing an extra factor of 1 over n. Whereas I know that even in free space, if I just calculate the free space chain numerically, I have eigenstates in there whose decay rates scale like 1 over n cubed. So why am I not getting at least 1 over n to the 4 scaling instead of 1 over n squared? And again, this is where just kind of knowing basic fiber physics or optical physics can really help. So imagine I give you 2 different optical fibers. Actually, how many experimentalists are there in the room who've actually ever touched an optical fiber? 1? Okay. So in the lab, you typically have different kinds of optical fibers. And if you take 2 different optical fibers, they generically have different dispersion relations or different effective refractive indices. So if you just try to slam one nanofiber one optical fiber onto the other, at the interface you have a dielectric mismatch, which means that when light guided in one nanofiber hits the interface is discontinuous, and then you can scatter light into 4 pi. Okay, so the bulk of the fiber is perfectly guiding, but if you take 2 different fibers and glue them together, you'll have an interface loss unless the dispersion relations happen to match. Okay, so you can just take that as intuition that maybe that's what's going on here. I start with an empty fiber, which is guiding a photon. I hit this new fancy atomic fiber, which should guide light perfectly, except it has a different dispersion relation. So then you can guess that when this fiber hits the first atom, that's where all the scattering into free space and where all the loss occurs. Okay, so that's the intuition. Yeah. Yep. Yeah. Yeah. Okay, so if you do work with experiments and different optical fibers, the solution in lab is simple. You just buy a fiber connector, which is designed to smoothly transfer the dispersion relation from one to another. So this is not, when you have this kind of fancy atomic fiber, this connector is not something that you can buy from a store. You have to make it in the lab. The details don't really matter. It turns out the way you can do that is just by tailoring the control field to be spatially inhomogeneous in space. So the idea is that you try to make the first atom very transparent to light or almost non-existent, and then gradually you turn on the atomic response to the nanofiber. So then you can go try that numerically, and now you can plot the error now on a exponential scale, and you see that as a function of atom number, the error actually decreases exponentially. Okay, so what the textbook told us as a presumably fundamental limit of error is actually exponentially wrong. You can find exponentially better ways to build a quantum memory. So what the set of slides I showed you here was actually a very personal story. Like that's more or less the order of things that we calculated and how we tried to understand what's going on.
Get like this exponential, we then also like have the simple change of the fiber if you smooth out
In principle, probably yes. Although to kind of prove it, that might be another question. Okay, so it's really this result here, this exponential, that really piqued my interest and kind of convinced me that in quantum optics we really most likely barely scratched the surface of what we actually understand of atoms and light, and the space of actually how powerful these systems are, and what we can do with it. Okay, so the rest of what I'll show you is really just trying to kind of build upon that idea. Trying to go beyond what the textbook says and figure out what's the true space of possibilities. Okay. Any questions on this part? Okay. So just to kind of recap where we are, as a phenomenological model, as phenomenological level, I argued that 1D chains can act as perfect waveguides. Then you can functionalize that into a quantum memory with an exponentially better error rate, error probability than what the Maxwell block equations predict. And then the next thing is I'll now describe how a 2D array can be a perfect mirror for single photons, and how to turn that kind of classical effect into a quantum one and build up a photon-photon quantum gate. Okay, so the way we formally solve it is the following. So let's actually take an infinite 2D array in the transverse directions. Now, once it's infinite, again, you can imagine solving or diagonalizing the single excitation manifold by Bloch's theorem. Okay, so Bloch's theorem says that if I define spin wave creation operators, or sorry, annihilation operators Sk, where k is the Bloch wave vector, then these kind of Bloch excitations or spin wave excitations, they should be the eigenstates of my system. So each spin wave with a wave vector k should have some complex energy. And then the point is that if I have an infinite system and I come in with a plane wave, which is also of course translationally has discrete translational invariance, then a given plane wave, its k vector is only going to couple to one of the spin waves of the system. So for example, if I take the k equals 0 spin wave mode, that's the mode where all the atoms or all the dipoles are oscillating in phase. And so if I come in with a plane wave at normal instance, which hits all the atoms in phase, that plane wave does not see the atoms as n independent objects. It's only going to couple to that one collective spin wave mode. So in principle, the problem becomes very simple because the problem separates in k space. Right? So if I choose again, if I choose an input wave with a well-defined value of k, there's only two states I can excite in this kind of weak driving limit. I either have the ground state, or I have one excitation in a spin wave mode with exactly the same k vector. So it's effectively something like a two-level system or a single mode linear oscillator. Okay? So in principle, it's quite straightforward to solve, if not tedious, and then we can go and reconstruct the fields. Okay, so that's how you mathematically solve it. But now let me kind of argue intuitively why the system should be 100% reflecting. So there's basically four ingredients. So just to be concrete, let's tilt the 2D array on its side and shine in light on at normal incidence. So the first ingredient is that atoms cannot absorb. They can only scatter. So in other words, a two-level atom, if you excite it, there's no other degrees of freedom of the atom to just eat that energy. The atom has to rescatter that light or turn it back into a photon. Okay, so all the energy I send in principle has to come out. When I have spatial order, you can think of this object classically as a Bragg grating. So if I have a Bragg grating, I shine in light at a well-defined direction. That Bragg grating cannot scatter light randomly into other directions. I can only create discrete diffraction orders. So as a first example, the fundamental order would just be direct transmission or reflection. I can have a first diffraction order into a well-defined angle, where essentially my lattice of atoms adds 1 unit of reciprocal lattice momentum, so 2 pi over d, to the light. The third ingredient is that if my lattice constant is too small, only the fundamental order is radiative. So in particular, if the atoms are trying to add 1 unit of reciprocal lattice momentum, 2 pi over d, at some point, d is going to be so small that this momentum becomes too big for light. So again, it doesn't match the dispersion relation of radiation waves anymore. Okay, sorry. And then the fourth ingredient is simply atoms have a resonance. Okay, so to illustrate that, let me turn this original problem. So I have a plane of atoms. I shine in light from one direction, and I can say that that's the coherent superposition or sum of 2 different problems. So one problem is where I shine in light from both directions, but where the light is in phase. And a second problem where I shine in, again, light from both directions, but in this kind of upgoing direction, I put a minus sign. So the light is arriving at the atoms out of phase with respect to each other. So let's look at this case first. So if the atoms sit in the z equals 0 plane, then when I add up e to the minus ikz and minus e to the ikz, that creates a node in the atomic plane. Okay, so basically in the atomic plane, these input fields cancel out, so the atoms see no light. If the atoms see no light, they can't be excited, so they might as well not be there. So in this case, I can conclude that these 2 individual plane waves transmit past the atomic plane with a transmission coefficient of 1. In this case, the waves combine to form an antinode at the atomic position. But this actually looks a lot like chiral waveguide QED. So again, I argued already from the previous slide that when I send light in, it can't disappear. It can't go in another direction. Okay, so the amplitude of the transmitted light has to be 1. Also, because of the kind of mirror symmetry, when these plane waves pass each other, they have to remain symmetric. Okay, so the transmission coefficient of this guy and this guy have to remain the same. So you see, it's very much like the chiral waveguide problem. Like the spatial mode of light is fixed. It has no choice but to kind of interact with the resonance of the atoms and pass it. And so then you pick up exactly a pi phase shift, like in chiral waveguide QED. So you take these 2 answers to these 2 separate problems, and you add them back up to find the answer of this problem. So as an example, if we want to calculate the transmitted light, we say that, okay, transmission is this downward field times a transmission coefficient of -1, plus this downward going field times a transmission coefficient of +1. I add those 2 things up, and I get my net transmission is 0. And likewise, you can conclude that the only thing that can happen is that 100% of the light is reflected. Okay. So this has actually been experimentally seen. Experimentally, what you can do is you can create a so-called Mott insulator. So this is an optical lattice, a 2D optical lattice of atoms with more or less exactly 1 atom per site. And then in the experiment, what they can do is they can simply shine in light. They have a CCD detector to try and they can try to catch the transmitted light and reflected light and just put it onto a CCD camera and image it. And then you get an image like this. So what they're plotting here is the reflected field in some normalized units. This dotted square, this dotted region here is exactly where the Mott insulating region of the atoms sit. So you see that exactly whether you have 1 atom per site, you get a very high reflection. So if you actually go look quantitatively, you see the reflection is not 100%, it's closer to 60%. Most of that is actually due to not kind of, like, what's the right way to say it? So basically the issue is that this experiment was not designed to be a quantum optics experiment. So they don't have the ability to, for example, shine in a focused Gaussian beam, really calculate reflection. So they have some part of the beam that's just bypassing the atoms completely and still getting a sense to the CCD. They shine in the light for too long, so the atoms scatter too many photons and start heating up. And so the fact that they see 60% reflectance is mostly due to those types of imperfections, which are not kind of, they're not really like challenging imperfections to correct in the future. Okay. Okay, so now you can ask, well, I have 100% reflection. Should I take that as a signature of, now I have 100% atom-light interaction efficiency? If I try to functionalize it. So the answer turns out to be yes. You have to be careful, though, because I have an infinite number of atoms. And even in the Maxwell-Bloch equations, if I have an infinite number of atoms, hypothetically, I can do everything perfectly. So here, you have to be a little bit careful and really talk about finite atom number. So for example, if I say I have an n by n array, then you really have to think about what does efficiency mean from an experimental standpoint. So in particular, in a lab, you can generate a Gaussian beam, whose beam waist you can choose. And with the same optics, you can easily collect light reflected, but only back into the same Gaussian beam. And then you can align optics so that you also collect any light transmitted into the same Gaussian beam or Gaussian mode. So that's what you can kind of realistically do in an experiment. And again, in an experiment, you can't catch 4 pi emission. So the transmitted field, the reflected field, they're just 2 discrete modes out of an entire continuum of modes in 3D space. And then you say that, well, anything that's not going into this Gaussian modes, I just simply have to treat as loss or effective absorption. Okay. And so then you can re-ask the question, if I have a finite-sized array and a beam waist, can I still get 100% reflection? The answer intuitively is no, because if I make my beam waist too big, then part of the beam will just bypass the atoms completely and be transmitted. If I try to focus my beam to be really tight, so even just hit 1 atom, for example, then it kind of makes sense that all these kind of collective interference effects should disappear. This should go back to the coupling efficiency of just a single atom in a Gaussian beam. So it's kind of clear that there's a kind of optimum beam waist you should choose. And it turns out if you choose that optimum beam waist, you get almost 100% reflectance with an error that scales like 1 over n to the 4th power. Okay, so that's just kind of reflection. And then playing the same game, you can now look at a quantum memory. So we can take light, we can shine it onto the array, do EIT, we try to take that photon and map it into a collective excitation. And then, not surprisingly, when you do the quantum memory for this 2D array, it has exactly the same error sources as reflection. So you can't make the beam waist too small nor too big. And then you can actually just, instead of abstract scalings, you can also look at realistic numbers. So as a function of linear system size, linear number of atoms, the blue curve here is the numerical error. And kind of what's remarkable is that if you in the lab just create even a small 5 by 5 array of atoms, which is certainly possible, in principle, that can already get you to less than 1% error for quantum memory. Okay, so this is to be compared with these experiments where they keep adding more and more atoms. At some point, you have 1 million atoms. You still have 10% error. You add even more atoms, and then your errors even start to go up again. Okay, so this really shows that maybe the future platforms for quantum optics might look completely different than what we're doing now. So maybe I'll take a few more minutes just to tell you how to implement a photon-photon gate, just to complement what I told you earlier today about the Maxwell-Bloch equations. And so the first question is, well, what if I just have a 2-level array of 2-level atoms? That is not obviously possible. So in particular, imagine I shine in one photon, and I see that it's reflected. So the fact that it's reflected means that one atom in that array had to have been excited, right, to emit the photon back to me. But because I have a two-level system, that one atom, which was responsible, is not available to excite a second time or to reflect a second photon at the same time. So just the fact that I see that one reflected photon, now if I try to send in a second photon, from the standpoint of that second photon, it effectively looks like I punched a one atom hole in my array, right? Because there's one atom in that array that cannot simultaneously reflect a second photon. So this gives you a sense that this mirror is intrinsically nonlinear, right? Because first I get perfect reflection for the first photon, the second photon sees a little bit of a hole that I can try to propagate through, but the point is that it's just a little hole. Okay? So if you want to make a photon-photon gate, so if you really want this first photon to have a giant effect, qualitatively it's clear that you want to punch a big hole. Okay? And that's exactly what Rydberg excitation or Rydberg interactions allow you to do. So recall that if I have Rydberg interactions, if I have one atom in a Rydberg state, then the energy shift of a nearby Rydberg atom goes like 1/d to the 6th power. If I actually want to use the Rydberg interaction for this atomic mirror to punch a big hole, it turns out that I don't want to use it. I only want to use it in a virtual way. So let me explain what that means. Imagine I shine in a first photon. I store it, so I really generate a Rydberg excitation. So then what I want to do is I want to, between the excited state and Rydberg state, I want to shine into control fields, but I want the control field to be way off resonance, so to be way off resonance from this E to R transition. So what that means is that the control field is not really able to induce true population transfer between E and R, but it can still have an effect within perturbation theory. So in particular, imagine that I had an atom far away, and it was sitting in the E state, hypothetically. So if I have an atom in the E state, and I drive the E to R transition, but at a big detuning, then within second-order perturbation theory, I can conclude that my eigenstate to lowest order is still an E excitation, but I just pick up this kind of extra energy shift omega squared over delta. So my excited state resonance frequency is now sitting at a slightly different point compared to a bare atom. Now let me consider an atom in the excited state, but which is much closer, so that the Rydberg levels start to interact. So now this Rydberg level is shifted up by a large amount. If it's large enough that Rydberg excitation, that Rydberg state effectively isn't even there anymore. And so therefore, this control field shouldn't do anything. So this excited atom, provided that it's close enough to this Rydberg excitation, would not see an energy shift. And so effectively what you're doing with this Rydberg dressing scheme is that once you have a Rydberg excitation somewhere in your medium, you're making atoms far away have an excited state resonance frequency, that's one value, and excited state atoms nearby to have another value. So you're effectively changing the resonance frequency of the atom as a function of position. So the way to turn that into a gate is the following. It's very much like the free space case. I first shine in a pulse A. If there's no photon, then I don't store it. All my atoms remain in the G state. If I shine in the first photon, if there's a first photon in pulse A, then I store it into a Rydberg excitation. I now turn on this Rydberg dressing scheme. And what that Rydberg dressing scheme does is it takes all the atoms in the vicinity of that Rydberg excitation, and it shifts the resonance frequency of the excited state by a large amount. Hypothetically, let's even say infinite. And so if the excited state frequency is shifted by an infinite amount, effectively those atoms are not there anymore. I've punched a giant hole around my Rydberg excitation. And now I shine in photon B. If there was no photon in A, then photon B continues to see a perfect mirror. If there is a photon in pulse A, then this photon B potentially sees this hole that it can transmit through rather than reflect. Okay, so it's an entangling operation in the sense that the direction of propagation of this photon B, whether it reflects or transmits, is conditioned on how many photons were in pulse A. So you can kind of believe that for this thing to work, this hole that you generate by Rydberg blockade has to be big enough that your photon B can fit through. So the limiting error will be determined by the size of this Rydberg blockade hole. Not surprisingly, the error scale is exactly in the same 1/r⁴ fashion. And so what I'm plotting here is the error of a realistic gate as a function of a Rydberg blockade radius divided by the lattice constant. And again, what's kind of remarkable is, even for a reasonably small Rydberg blockade radius of just a few sites, which is certainly realistic to do in lab, again, we're already talking about a quantum gate for photons with an error that's less than 1%. Again, that's to be compared with current state of the art, where the errors are over 50%. So here I really just talked about fundamental sources of error coming from light scattering into 4 pi. There's any number of other errors, imperfections in the lab that you might consider, either the motion of atoms, maybe in my mod insulator I don't have perfect filling. I have to consider a more realistic Rydberg dressing, how well can I do that in practice? And we believe that if you do all these honestly, those types of errors should also be at the 1% level. So in other words, a photon-photon gate with an error of around 1% or a few percent, does seem to be realistic, provided that you really exploit wave interference in quantum optical arrays. So again, some aspect of this has already been seen experimentally. So they haven't been able to they haven't been able in the same experiment to implement a photon-photon gate per se. But they can see that if they just kind of create by hand one Rydberg excitation inside that mod insulator, it can really change the behavior of their atomic mirror. So here's just the case of the usual 2-level atoms. You shine in light, you get this very high reflection. Then what you can do is you can take this one ancilla. So this is just 2-level atoms. You can instead do EIT on the same lattice, then you get perfect transmission. And then if you try to do EIT, but you flip one atom to a Rydberg state, you see that around the Rydberg atom, all those atoms actually become reflecting again. So this one flipped atom is able to create a mirror over a macroscopic region. So again, this is not quantum optics per se, or it's not a photon-photon gate per se, but it illustrates the main ingredients of the physics. Okay, so with that, I think that kind of closes the loop, if you want, on what I presented earlier today. So I showed you the Maxwell block equations. What are the best errors that we know of if you try to do a quantum memory or a photon-photon gate? I then showed that if you take arrays of atoms and really account for wave interference, you get some pretty interesting phenomena that you would not expect from Maxwell block. And it's not just kind of interesting phenomena, but then you can turn it into real applications. Quantum memory with an exponentially better error rate, and a photon-photon gate with a polynomially better error bounds. Okay, so I think this kind of suggests as a potentially very different future for atom-light interfaces compared to what we're building now. So I guess that more or less kind of concludes today. And then next time, I'll try to give some examples of more kind of strongly correlated or emergent phenomena at the many-body level. So any questions on what I presented?
So regarding the experimental platform, you think it's so the way forward is to Mott insulator in optical lattices, or also tweezers, available options? Or?
Conceptually, yes. So one thing that
also, if there are people already doing it that it would be nice to know.
No. So I would say that the best experience so far really from Emmanuel Bloch's group with these Mott insulator. So if we want to be serious actually about building a quantum optics interface, there might be reason to think that maybe this mod insulator isn't ideal. So in particular, one nice thing about the mod insulator is you almost get for free this 1 atom per site with this subwavelength. I mean, that of course is great. The problem though, or maybe two problems, which I see are on one hand, to build, so this mod insulator is really the same as creating a quantum degenerate gas in an optical lattice, which is actually a lot of work if you want to just do quantum optics, right? So in other words, like, when people do a usual quantum memory and atomic ensemble, the atoms are cold, but you don't really have to go through the extra work to put them in a lattice or do a BEC. And here it's like you're doing all this work, of Bose-Hubbard physics. At the end, just to forget about Bose-Hubbard physics to create a mod insulator and then shine in light. So that seems a little bit like kind of overkill in terms of complexity. And also it's a lot of, it's very expensive to build. The other problem is like, it takes a very long time actually to form this mod insulator. So the cycle time, like you create a mod insulator, you shine in some photons, the atoms heat up, and then you want to hit a button and create another mod insulator to do another experiment. I think in that block experiment, that waiting time between one mod insulator and another is actually like 10 seconds or tens of seconds. So you can't shine in, or you can't do a lot of experiments per unit time. And so I think at some point that's really just going to limit you in terms of if you want to collect statistics of photons and measure photon correlations. If you barely have any statistics in the first place, that makes those experiments very tough. So either people really have to figure out how to make mod insulators much faster, or maybe use somehow tweezers, which are potentially much faster to create these subwavelength arrays. So it's not completely trivial experimentally, but those are things to think about in the future, I think.
More questions? Okay, there are no more questions. Thanks, Darrick, for the excellent lectures today. Okay, so we come back tomorrow morning.